discuss why do we need this ultra shallow junctions. As we know, day by day we are shrinking our wafer sizes to decrease the total area. So there exists a need to not just this horizontally, but even the vertical decreasing of this size of the wafers must be done. Because I mean, as we form the short channel devices, okay, we are decreasing the wafer sizes in the sense we are making short channel devices. If we are making the short channel devices, the main thing that we, so if you are decreasing the channel length between the drain and the source, the main problems that we face are the decrease in the threshold voltage. That is one of the problems, and another problem is the drain-induced barrier limit. So first, okay, fine. What happens if this threshold voltage is reduced? Okay, I'm saying we are reducing the size of this channel, so it is leading to the reduction in the threshold voltage. Okay, fine. What happens if this threshold voltage is reduced? In fact, if you just see it without thinking, okay, voltage is getting reduced and that's better, you think. But if this threshold voltage is reduced, it leads to okay, fine. There's always a flow of this sub-threshold current in a MOSFET. So if this threshold voltage is reduced, this current starts, I mean, there will be a leakage, I mean, this leakage current increases as we reduce the threshold voltage. And other than this, the other one is if you increase the voltage on the drain side, it leads to an effect called drain-induced barrier limit. What is this drain-induced barrier limit? If you increase the voltage on the barrier side, I mean the drain side, even this leads to reduction of the threshold voltage. So even that is also leading to, finally the same problem, that is leakage currents. So to avoid this, because there are this threshold voltage and these problems, we cannot stop shrinking our sizes, because we need our wafers to occupy lesser space. So we have to proceed in such a way, we have to design our wafers or our MOSFETs in such a way that we have to shrink their size, but there shouldn't be any disadvantages because of that. So keeping this in mind, we have to think of possible ways of reducing, avoiding this reduction in the threshold voltage. So we have to try increasing this threshold voltage so that there will be minimum leakage currents. So if you see, this is the relationship between the short channel effect, that is the reduction in the threshold voltage, and the DIBL is drain-induced barrier limit. So if you see this, we can see that these short channel effects are directly proportional to your thickness of the oxide, thickness of the depletion region, and Xj is my junction depth. So you can see that this is proportional to all of these. So now we want minimum short channel effects. So we want minimum short channel effects so that our VTH will be high. To make our VTH high, we have to either so we have to reduce the short channel effect. So to reduce that, we have to either reduce this oxide thickness. Okay, we have to either reduce the oxide thickness or the depletion layer thickness or the junction thickness. Junction depth. You have to reduce either of these to increase your threshold voltage. So first, let us take a look at this reduction of this oxide thickness. The oxide thickness, that is which we use from the gate to the wafer, that oxide thickness, what is there, you can reduce it to reduce the short channel effects. But we have reached a stage where we have already reached a stage of 1 nanometer. Our thickness presently, which we are employing in present technologies, is 1 nanometer. So we cannot go below that. To go below that, you will have to use some other oxide. Instead of the conventional silicon dioxide, you will have to go for something, and research is being done there, but it is not yet successful. So we have already reached the saturation limit of 1 nanometer. So there is no chance of reducing the TOX. So now come to the depletion thickness. Yes, this depletion thickness can be reduced by increasing the dopant concentration in the channel. But that will, if you increase the dopant concentration in the channel, that will reduce out the mobility of the. So this is the one. You can see TOX, and this is this one, junction depth. So if you increase, the mobility will decrease. If the mobility decreases, the speed of our MOSFET decreases. So therefore, we cannot even reduce this that is depletion depth thickness. And the other problem is we have reached the saturation level. Even in this, we have reached around 0.6 into 10 power 18 of this doping concentration, so we cannot go beyond that. And so the only possibility that is left to reduce these short channel effects is the reduction of the junction, the junction depth, the XJ. So so now my main topic is how do we form that shallow junctions so that the short channel effects are reduced. So first, a shallow junction is basically formed by, first we incorporate the dopants, then we activate the dopants by annihilation process. So this is how our shallow junctions are formed. So when we do the implantation, when we introduce the dopant, the major problems that we face is, one is the ion channeling is one problem. Ion channeling is like in a specific direction you will have no opposing force, so that whatever dopant you introduce into the silicon, it just slides down to the deep, to the deepest regions. But we want just the shallow junctions, so we have to reduce this ion channeling. To reduce this ion channeling, so ion channeling exists only in crystalline structures. So this crystalline structure, what we do is we pre-amorphize with with some other, either silicon or germanium, so that to reduce this ion channeling. But the problem that occurs when you pre-amorphize is, if you'll have a polycrystalline and a crystalline structure, if this this thing comes and you'll form a junction there. If this thing comes inside of your junction, that is if it comes somewhere in between this, as we pre-amorphize this crystalline structure and this amorphous structure, they both don't get into contact 100%. There will be some gaps. So if that gap comes in this junction, so that in this junction, that will lead to leakage currents, obviously, which is the result of lower threshold voltage. So we have to check for removing this ion channeling. And next one is the other problem which we face is the transient enhanced diffusion. This transient enhanced diffusion is nothing but interstitial. There is a mechanism called interstitial diffusion. If you suppose diffuse boron into silicon, it goes by interstitial diffusion mechanism. Interstitial diffusion mechanism is nothing but you will have lattice spaces in between in your silicon structure. So our boron goes to those lattice spaces. But even in the deeper region, you will have those lattice spaces. There is a chance that boron can go till deep. It can go very deeply and cause again the normal junctions instead of shallow junctions. This is another problem that we are facing. So firstly, let us see at the various doping techniques that we are employing in the present day. So these doping techniques, we have three of them: plasma doping, infusion doping, and molecular implants. In this plasma doping, what we do is we take the silicon wafer in a plasma region and we introduce gases into that chamber. Some gases such as BF3 or PH3 gases into that, and we ionize we give negative supply to our wafer and ionize the gases so that will attract the dopants, and we get dopant deposited on our silicon structure. But the other problem is, whatever materials are in the chamber, all of them get deposited on the wafer. So there is a chance of impurity. So we go to infusion doping. In infusion doping, what we do is we use a gas cluster. We make all the ions as a cluster, and what we do is we force that cluster to hit our, we charge it and ionize it and release it. So it goes and it hits the wafer surface, and then it transfers its energy. So after ionizing our molecule, the atoms whichever we want, they will go and diffuse inside and they will intermix with the silicon. So that is how this infusion doping is done. Next, so as I said, the formation of shallow junctions, you need first doping, and then you will have to anneal this dopants whatever you have introduced. Then we go for annealing techniques that are presently being utilized. One is the regular process, rapid thermal processing, which I learned even in our class. This is the most common type of annealing technique. But the problem with this technique is that we'll have to expose our wafer for so much time. So that leads to deeper region formations, which is not desirable because we want ultra shallow junctions. Okay, what do I mean by ultra shallow junctions is we need junctions of thickness of 10 nanometers. 10 nanometers means for 32 nanometer node technology and below. For that technology, we need a shallow junctions of just 10 nanometers. For 45 and above, I mean, you need just 20 nanometers or above junction depth. So to form this 10 nanometer, if you expose it during annihilation process, if you expose it for too long, these dopants, whatever they are there, they diffuse in and form deeper regions, but we don't want that. So we go to spike anneal. Spike anneal is nothing but it gives out high energies at instances for in very short interval of time. Even this has some this is actually good, but this is employed only till 45 nanometer because it's able to achieve only 20 nanometer of junction thickness to the maximum. So we cannot go beyond that. Next, we employ flash annealing and laser annealing. These are the most advanced techniques which are not commonly used. These have come up very recently. So in flash annealing and laser annealing, what we do is we use flash lamps which are given very high voltages, and they give out the flash for just microseconds of time. When you give out for microseconds of time, the dopants, they don't diffuse too much inside. You'll have shallow junctions, but the problem that here is because you give the heat for very less amount of time, this dopant, I mean, it may not get annealed properly. There may be some defects caused, and even by these methods also we are able to achieve just 15 nanometers depth of these shallow junctions. So, but our requirement for 32 nanometer technology is below 10 nanometers. So that is the problem that is being caused even by flash annealing and laser annealing. These can be used to achieve partly the shallow junctions, but not completely shallow junctions. So whatever technology that we have till date, there is no technology which can go below 10 nanometers junction. So this is one of the major problems that the industry is facing presently, and there are many researchers going on this. They have come up with one of the solutions of silicon and insulator, where they place the insulation layer I mean on the very top, I mean at a depth to which we need the junction, and below that, so that the heat doesn't pass below that because of this. But even this is not completely developed. So coming to my solution, what I am giving to this problem is, what I say is, you take a wafer, you dope it, you do annealing. During annealing process, you heat it from the above, so that the dopants diffuse inside. But now the problem is these dopants are diffusing too much because of the higher heat and longer time. So what I want to say is, why don't we cool, I mean, while you are doing annealing from top of the wafer, at the same time what I suggest is, why don't we cool the wafer from the bottom to such a level that only till where we want the junction depth, so that the heat doesn't flow, I mean there will not be any heat beyond that point, so that the dopants, they will not fuse inside. So we can just form the shallow depths, which is our requirement. So this is my, I mean, I don't know to how far it works. This is just what I thought. So the conclusion is, like, if you form these shallow junctions, you can reduce the size of the wafers, you can reduce the cost of manufacturing, which are actually very advantageous things. So these are my references. Yeah.
So how one of those technologies is very interesting, flash annealing. So how is that different? Like, is there a reason you would do that over laser annealing?
Actually, laser annealing is more advanced compared to this. Yeah, but what you do in laser annealing is you give very high voltage in very small instance of time, in microseconds of time, and you give I mean, generally you do it with single source, but in laser annealing what you do is with different sources, with all around, but very small instant of time, so that you will cover the entire area. So that is how you do it. But because we are doing it for very, very small amount of time, the defects won't get cleared that completely.
Because I'm confusing, so can you explain again why we need to increase threshold voltage?
What? Threshold voltage. Actually, the threshold voltage reduction is being caused because of the saturation length. As we decrease the channel length, you will have a capacitive coupling between the source, drain, and the gate terminals. Because the length is the distance between them is very small, there will be capacitive coupling between all of them. So because of this capacitive coupling, there will be a reduction in the threshold voltage. So if this threshold voltage is reduced, you'll have a subthreshold current which is present in the MOSFET. So if this voltage becomes too low, this current becomes high. That means it starts leaking more. So it leads to leakage currents. which is not really good. It doesn't allow our MOSFET to function the way we want.
Okay, so you're trying
So
to increase
we doesn't want this threshold voltage to reduce even when we use short channels. So we have to increase this threshold voltage without even by scaling down the MOSFET. So how do we do that? One possible way is by reducing the depletion depth.
So laser, do you think will have very narrow?
Yeah, it has, but it is what I have read is it is achieving only up to 15 nanometers of depth, but we want 10 nanometers below. But at the cost of increasing the sheet resistance. This other trade-off is sheet resistance. As we reduce this junction depth, the other trade-off is it leads to increase of sheet resistance. So that is the problem with the laser engineering.
If I'm not wrong, what you're proposing is we heat up the wafer from one side and cool it down from the other side.
Yeah, that is my solution. Like annealing, we do the normal annealing thing. So in annealing, what we are doing is we are going up to temperatures about 1200 degrees Celsius. So what I say is, why don't we cool it from bottom to such a level till where we want the depth, junction depth.
So what the question is, what's the contribution of the thermal coefficient of the material, of the substrate in your proposition? Because if the thermal coefficient is
So
too much,
contraction and expansion on both
Yeah.
sides, it may lead
We
to
might get
extra
crack.
stress.
we might get a crack.
Yeah, that is also possible. That is one trade-off with that thing.
Okay.
Actually, this is not being implemented. This is what I thought. So
Right? Thank you.
Hello everyone, my name is Rudy. Today my topic is a new approach to lithography resolution enhancement. So here's my outline. First I will talk about a little bit on the motivation, then I will give the background of critical dimension. I will show you a super resolution experiment, then will be my design for 193 nanometer lithography. At last will be the conclusion. I'm sorry. So the Moore's law tells us the number of transistors on the chip will double every 18 months. So the more transistors on the chip means a better performance and a low cost per transistor. So scientists and the engineers are trying to make the laws more alive. So they trying to decrease the decrease the size of the transistors. So the direct way to reduce the size of the transistor is to increase the resolution of the lithography systems. So this expression is it's for the critical dimension. I think all of you guys were very familiar with this, so I will not talk it too much. So they have some approaches to reduce this critical dimension or pitch limits. The most common way is people try to use light source with a shorter wavelength. In the past few decades, the wavelength has decreased from 400 nanometer to about 200 nanometers. Currently, people are using, I think they are using 193 nanometers. Maybe in the future they will use 157 nanometer light source. Another approach to reduce the critical dimension is instead of air, people are trying to use some medium in the lithography systems, so which will increase the refractive index, increase the numerical aperture in order to reduce the critical dimension. The first generation fluid is water, is just water, which increased the refractive index from 1 to 1.4, 1.5. Now people are trying to do research on the second generation fluid, which has the refractive index of 1.6, and 1.65. And people also think about the next generation fluent, which should be 1.8 refractive index. And another way to increase the numerical approach is to make a perfect optical design to increase the incident light angle, which also will increase the numerical aperture. So they also have other kind of technology like double patterning technology, which has been discussed in the previous lecture. But all this, I think this technology they have some shortcoming. For this one, the light source, it is very expensive to use a new light source with a short wavelength. And if you want to use a new light source, you also need to change all the optical systems. And for this guys, for the immersion lithography, I think the improvement on the critical dimension is not so much. See, even we can make the third generation refractive index the improvement is just maybe 20%. So the basic problem is that the critical dimension is still limited by the diffraction limit, which means that the critical dimension is determined by this expression. So people are thinking about is there a way to go beyond this expression, go beyond this limit? The answer is yes. Before I talk about that, we also I think we need to understand how this diffraction limit comes from. So here is the expression of the electric field. It is a superposition of many electric field with different wave number. Here K means wave number here. So in the Maxwell equation, there is another condition also need to be satisfied. This condition. This condition. Omega here means the angle frequency of the light source, say its speed of light. So for all these wave numbers, they have some high vectors, which means the kx squared plus ky squared is less than this number. This number, we call it low vectors. The kz will have a real number. So but for the high vectors, which this one is larger than this guy's, the kz will be the imaginary number. So if we substitute this kz into the original expression, we can see that the part of high vectors will decay very quickly because of the exponential part. So in physics, the part of with high vectors, they are called the evanescent waves, and they decay exponentially with distance. So which means no matter how perfect lens you make, this part, the evanescent waves will decay very fast, and the evanescent wave also carry the information of high vectors, which means you will lose this information. That causes you can never reconstruct the object you want, the original object on your image. So Pencher, a professor in UK, present a scheme to construct those evanescent waves by using a medium with negative refractive index. So here is his ideas. Between the object and the image, there is a medium which has negative refractive index. There's a lot of theoretical calculation inside, but finally the conclusion is that when the magnetic permittivity and the permittivity equal to -1 for evanescent wave, the transmittance function will equal to this guy's, which means the amplitude is still 1. You can say still 1, only the only phase change. So we still can get all the information of evanescent wave on the imaging on the image. So the physical mechanism behind this equation is that the evanescent wave decayed in the field in the first field distance, and it will be amplified by this medium. So that's why we can got the evanescent wave, but not without any loss. That's the mechanism behind this equation. So the problem we have is how can we find a material with negative refractive index if unfortunately we cannot find both magnetic permittivity and permittivity be negative for any nature materials. But fortunately enough, we can find some materials like the silver, gold, and copper, which show some negative permittivity in some wavelengths. So, and in those materials like silver, the magnetic permittivity is not so important. So what we care about is only the permittivity. So only if we can find the negative permittivity here, we can use it to make a superlens to reconstruct the evanescent wave. So here is the permittivity of the silver. We can see when the wavelength is larger than about 300 nanometers, the permittivity will show some negative permittivity. Will show some become negative. There's another issue about the silver because it's a metal, so the transmittance is very important because we know the metal is not transparent. So, but fortunately, we are going to use some very thin film for this metal, so they'll have relative high transmittance. Here is the transmittance for some different thickness of silver film. You can see around 300 nanometers, the transmittance is still quite high. So which means we can use this material to make superlens. So here is, as I know, this is the first experiment to show the super resolution by using a superlens. So here is what they do. This is the it's a mask made of chrome, and after that it's a PMMA. It's a transparent material which has 40 nanometer thick. After that it's a layer of silver which has 35 nanometers. This layer of silver works as a superlens, and it will transfer the pattern on the mask into the photoresist. So here's the experimental result. Picture A is the imaging of the mask. Picture B is the imaging of the photoresist with super lens. But this one is without super lens. So the difference is quite obvious. So here is the cross section of the photoresist. We can see the line with the red lights for without superlens and blue lights for with the superlens. We can see that if without superlens, the line with of the pattern is about 300 nanometer, which is very close to the wavelengths they are using. So which means this line is still limited by diffraction limit. But for this, with superlens, if we are using a superlens here, the line width will be much smaller than this one. It shows the super resolution. I mean, it's go beyond the refraction limit. So in their experiment, they are using the source of 300 nanometers. So I'm thinking, if we can use this kind of, we can do the same thing if we are using 193 nanometer lithography, which we are using currently. We can get some better result, some higher resolution. That's what I'm thinking. But the first problem is to find very good materials which can work in this case. The silver will not work because when the wavelength is below 200 nanometers, the permittivity is become positive for silver. But here's the permittivity of gallium arsenide. The solid lines it's the real part of the permittivity. That's what we care about. So we can see around 200 nanometers, it shows some negative permittivity, and it's quite high. And it's quite high. And another issue is also about the transparency, and the transparency of the gallium arsenide is also relatively high. So which means in theory we can use gallium arsenide as a material to make a superlens in this wavelength. So different with only a single film, I also use another kind of design which called one-dimensional mental dielectrical photonic band gap structure. So in this this structure is made of two kinds of material. One is gallium arsenide, which works as a lens. Another one is magnesium oxide. It works as a dielectrical medium. So on the top, the design is like this. On the top and on the bottom, there's 5 nanometer magnesium oxide with anti-refraction coating, and in between them is 8 nanometer and 10 nanometer magnesium oxide. So the advantage of using this kind of structure is two advantages. One is avoid the effect of dissipation, because if we are using only one single film, which means we need make this kind. This one is very close to our ideal lens, but in practical they have some absorption loss exist, so it will not so perfect, which will cause some dissipation. But if we are using several layers, so they will form an amplification distribution. So each of the layer will give a little contribution to the amplification. So which means for each layer, they don't need to satisfy very extreme condition, and which will reduce the dissipation greatly. Another advantage is this kind of structure can enhance the transmittance, because the reason is that those layers can work as fibropyro cavities. So there will be some resonance existing between them, which can enhance the transmittance. So here's my conclusion. Review on methods to reduce critical dimension, explain diffraction limit, active index medium, and introduce a new approach to enhance lithography resolution. A design for 193 lithography. And here's my reference. thank you. Any questions? Yeah.
Two. First of all, who was it who did the super resolution experiment? Which
Patrick.
was it?
You mean who's the guy who?
Yes.
Present. I will show you this guy.
Henry.
Yeah.
Also, when they did that experiment, was what they constructed an actual lens? I mean, does it have a focal length? Was it focusing something, or is it?
I think there's no, because it's very close to each other.
So it's a layer,
Yeah.
and what it's doing is it's extinguishing some sort of diffraction caused wave. Is that a correct way of looking at it?
Can you say it again?
What exactly is this layer of material doing that they constructed?
You mean how this lens works?
Yes, because it's not focusing anything. What's it really doing? So I mean, I have my pattern. Light passes through it. Then what happens?
Because for the conventional lens, I see the high Victor part will decay very quickly. Okay, can you see that?
The what part?
The high Victor part,
I see.
which also called the evanescent wave, they will decay very quickly.
Okay, so this preserves
Yeah,
the
it's-
evanescent wave.
yeah. So these guys can work. Actually, it works as an amplifier. It can amplify the evanescent wave. So, so if you put
Okay,
material,
amplifies it, okay.
So my question is, the silver has refractivity, negative refractivity.
yeah, in some wavelengths.
In some wavelengths.
Yeah.
So the net. Okay. So can you give me number? So what?
I have curve here. This is I draw it. There's a expression on this paper. Pen paper. They give an expression for the permittivity of the silver, which is the function of wavelengths. If you change, you can find it in this paper. It's a function of wavelengths. So you change the wavelengths, the permittivity also changes.
So refractivity doesn't depend on thickness of silver layer.
No, no,
Just
no.
to
Yeah,
just
no.
specific wavelengths the silver has.
Yeah, the refract index depends on the dielectric permittivity.
Without any process specific. So just
Okay, good afternoon everyone. I'm Mohammad Razil Hassan and the title for my term paper presentation is Graphene Nanoribbons as a replacement of copper interconnects. I hope the title is simple enough to explain what my main goal is, that there is copper interconnects and I want to introduce a new material called graphene nanoribbon to be used as replacement of copper for interconnections. And to explain in more detail, I have divided my presentation into several segments. At first, I'll give you an introduction of what interconnects is, why copper has been used for so many years as an interconnect material, and what interesting features does graphene nanoribbons have that I'm proposing to replace copper with graphene nanoribbons. And with that, I'll conclude my presentation. So quick start. Interconnects are conductor line connecting elements of an integrated circuits. In other words, this is just the internal wiring of an integrated circuit. And if your integrated circuit is too much dense, then the researchers use multi-levels of interconnects. For example, in recent Intel's 35nm technology, they are using 8 layers of copper interconnects that is being used in the dual-core Intel processors these days. There are some key features that we look for while choosing an interconnect material. So first, that it has to have a low resistivity. The second, it has to have a higher resistance towards electromigration. Now, electromigration is the transport of material inside the substrate due to the movement of electron. For case of interconnects, as current passes through interconnects due to the movement of electron, the metal ions actually diffuse through the substrate. And since silicon is the most commonly used substrate these days, for so many years, there's the third point comes, the interconnect material must have less diffusivities in silicon and dielectric material. Now, copper has been used for its own advantages for so many years as a multi-level of interconnects. There is a chart comparing the resistivity of several metals. As you can see, copper has the second lowest resistivity. Of course, silver has the lowest, but in some cases, silver was used for interconnects, but it has a very low electromagnetic resistance. That's why most of the cases they use copper. And again, gold is expensive. In some cases, people use alloys of copper and aluminium also for interconnects. But with so many benefits and drawbacks, copper was the most beneficial choice so far. So far, the performance of copper was sufficient to be used as interconnects. The limitations come as we decrease the size down. With time, as you know, the size of the integrated circuits is getting smaller and smaller. And copper is a metal, right? If you decrease the cross-sectional area or the width of the thickness of any conductor, the resistance increases. And so happens for copper also. And again, copper shows weak adhesion to silicon when we are considering very small size. Second, copper is also called a very effective poison for silicon. You see, as current passes through copper conductors, the copper ions diffuse to the silicon substrate. Because of this reason, in most of the cases, they use titanium or tungsten layer that works as a diffusion barrier for the interconnect and substrate material. Then, under stress condition, copper forms void. Suppose on the left figure, this is a schematic diagram of a copper conductor. The gray region represents the conductors. And in here, you can see that there is formation of voids in the copper conductor. These are under stress condition, and I believe this is the dimension is around 50 nanometer. And last, it's a metal. And as we know, if we increase the temperature of a metal, the resistance increases due to the increased number of collision. So here comes graphene nanoribbons. Graphene is just one atom thick planar sheet of carbon, and graphene nanoribbons are nothing but just thin strips of graphene sheet. On the left, it's a figure of a single sheet of graphene, and in the middle, these are some graphene nanoribbons. Typically, the width of the graphene nanoribbons vary between 5 to 100 nanometer. And there are actually two types of graphene nanoribbon. One is the armchair graphene nanoribbon, that is AGNR, and another is the zigzag GNR. In the top figure, as you see, the edge pattern of the graphene nanoribbon is zigzag, and these are named as zigzag graphene nanoribbons. And in the bottom figure, the edge pattern is different. These are called armchair graphene nanoribbons. Typically, all zigzag graphene nanoribbons are found metallic, and armchair nanoribbons can behave like semiconductor and can behave like metals also. It depends on their chirology or the orientation. Now, here's the most powerful point why I want to use graphene nanoribbons for interconnects. Graphene remains highly stable and conductive even when it is cut down into very small thin ribbons. And as I said before, for copper conductors, for metals, as we decrease the width of the conductor, the cross-sectional area of the conductor actually decreases, and so the resistance increases. In this figure, it's a diagram with resistance per unit length versus width. And as we decrease the width of the conductor, this is the curve for copper wire, the resistance of the copper actually increases exponentially. But this is not the case for metallic graphene nanoribbons. They show some very unique, interesting properties. This is the curve for metallic graphene nanoribbons. As you see that the resistance of the graphene nanoribbons does not increase that much with decrease in the width. And according to the International Technology Roadmap for Semiconductors, interconnects on scale of below 14 nanometer is predicted to happen within the next 5 years. And from this point of intersection, you can see that below 8 nanometer, graphene nanoribbons actually outperforms the performance of copper in terms of resistivity. The second point is thermal conductivity. Now, with faster clock speed, the power dissipation of integrated circuit is also increasing. A quick solution to that is to use such a material as interconnect that has a higher thermal conductivity. Now, thermal conductivity is the property of a material's ability to transfer, to spread the heat. Now, if you can see from this chart, metallic graphene nanoribbons actually have 100 times more thermal conductivity than the conventional copper. That means if the interconnects are made with graphene nanoribbon, it can spread away, it can transfer the heat 100 times faster than the copper. So you can say it's like 100 times cooler than copper. The third interesting point is thermal quenching of resistance. An experiment was done with graphene nanoribbons of width around 20 nanometer, and they observed that if we increase the temperature of monolayer and multilayer graphene nanoribbons from 300 to 500 Kelvin, the resistance actually decreases. For single layer graphene nanoribbon, they decrease around 30%, and for multi-level, they decrease up to 70%. Here is a curve showing the current and voltage relationship of graphene nanoribbon resistors. The upper curve is for the 525 Kelvin, and the lower curve is for 300 Kelvin. So as we increase the temperature from 300 to 525, the slope of the IV curve actually increasing. That means the ohmic resistance is decreasing. And if we consider the multi-layer graphene nanoribbons, the resistance dependence on temperature is even more. The last but not the least point is the capacitance of graphene nanoribbons. It is expected that ultra-thin graphene nanoribbons will show 3 to 4 times less capacitance between interconnects than the conventional copper because of their unique structure, their larger mean-free path, and less scattering in graphene nanoribbons. Not only that, the variation of the capacitance for graphene nanoribbons is expected to be around 70%, in contrast to 230% that occurs for copper interconnects. Now, I did not find any direct research that deals with the capacitance of graphene nanoribbon interconnects, but one experiment was done to compare copper wire versus monolayer single-wall carbon nanotube. This is the experimental setup where they use several conductor lines in a dielectric material, and they use the setup to compare the line-to-line capacitance, line-to-ground capacitance, and all that. And if you compare the values, you can see that the single-wall carbon nanotube actually offers around 4 times less line-to-line capacitance than copper wires. And graphene nanoribbons have very similar to single-wall carbon nanotube, because if you just unfold a single-wall carbon nanotube, that works as a graphene nanoribbon also. Suppose this is a single-wall carbon nanotube, and if you unfold the tube, if you cut it from here, that actually gives you a graphene nanoribbon. So it is expected that graphene will show similar behavior as like to carbon nanotubes. So it is expected that it will also have less capacitance. And with less capacitance, it will also consume less power with less delay and less crosstalk. Resistance are important if we consider the power dissipation or the heat generation of an integrated circuit. And capacitance are concerned for controlling the delay of signal, how faster the signal can transmit in the integrated circuits. So capacitance is a very important factor for ICs. Now, a few years back ago, it was not very much feasible to fabricate or pattern graphenes But this is not the case now. There are several recipes that researchers use to fabricate or pattern graphene. One is to use hydrogen etching to obtain a very flat surface, and then they use graphitization on that under a very high vacuum. Then something called electron beam patterning is used to pattern the resist coat on the graphene layer, and low power oxygen plasma etch is used to etch away the graphenes to transfer the pattern in the graphene sheet. This is a micrograph where they use this electron beam patterning, and this shaded area are the region where there is graphene and the white parts are etched away with low power oxygen etch. There are some more figures. Another team used STM lithography, scanning tunneling microscopy lithography, to obtain graphene nanoribbon features like this, where they obtain as thin ribbon as 10 nanometer with longer around 120 nanometer. Not only that, with this technology, you can actually have an angle in the interconnect, in the graphene pattern. And very recently, in last year, in 2011, researchers in Georgia Tech University, they fabricated this kind of structures, a number of parallel lines made up with graphene nanoribbons. These are as thin as 20 to 50 nanometer and length as high as 1 micrometer. So now see, this is quite feasible these days to pattern and fabricate graphene interconnects. Now you must be wondering, if graphene has so much interesting properties and this is so much feasible, why don't we have graphene interconnects in the processor of our cell phone or laptops? Obviously, there are some challenges. The first is, not much research have been done on the multi-level interconnect of graphenes that is already being used with copper interconnects. And second, as I told you, the capacitance of graphene interconnect needs some further studies. I have not found any direct studies with graphene interconnect based on their capacitance. And again, the fabrication technology is already set up with the metal deposition technique that use conventional metal like copper. And the whole system has to incorporate this new technology, the whole system has to modify accordingly. So there are some issues. Now, at this point, I'd like to conclude my presentation saying that with these interesting properties that makes graphene nanoribbon a very strong potential candidate as a replacement of copper. And I believe it's not so far that from now that we'll overcome these challenges, and very soon you will be having graphene interconnects in our regular electronic devices. I'd like to thank Dr. Samar Iqbal and our GTM Mr. Azhar Ilyas for their feedback and comments on my term paper. Here are the list of references that I've used for my research. Thank you for being patient. If you have any questions. Yeah, sure.
I think you mentioned this earlier, but I may not have caught it. What's the resistivity of graphene like?
What's the?
Resistivity compared to copper.
Okay. I'm sorry, I must have missed the point. It's around 400. As far as I remember, I don't know the exact figure. It's around 400.
Okay, so it's a little more resistive than copper, but much better thermal conductor.
Oh, sorry, I forgot. It's around 0.4.
0.4. Oh,
sorry.
Oh, nice.
So I have a question. You are using to fabricate electron beam lithography. So how do you get the time for regular chip? How long it takes?
Okay, as we know that electron beam lithography is a serial process. It takes a much longer time than the direct projection lithography. But with that limitation, these are all the advantages that we can get.
You think that electron beam speed is proper for current?
Yeah, obviously electron beam lithography takes some more time compared to the projection lithography or the conventional lithography that we use, the photolithography. But there you have all these advantages also.
Are there
Some
chemicals that
trade-offs.
can etch graphene?
Sorry?
Are there any chemicals that can etch graphene?
I'm not. Yeah, the technique is called low power oxygen plasma, but I don't exactly know what the chemical reaction is.
Okay, I don't know about the interconnection. So, is it important the bandwidth? So, is the capacitance like a low pass filter? So, there's.
I think the bandwidth is more important if we consider building switching circuits or transistor with that material. But as far as interconnects are concerned, we just want to use it at conductors. So we are more focused on less resistance and higher thermal conductivity and all that.
Is Isn't RC time constant important for interconnects?
So
Isn't RC time constant important for interconnects?
yeah, that's why I said that it's expected that graphene ribbons are supposed to show less capacitance, but I did not find any direct research that deals with this capacitance.
So low capacitance and low resistance,
Yes,
right? And how do we define time constant?
it's RC for a
1 over
time
RC.
constant for a series RC circuit.
Right. So how do we define what is RC time constant?
That the time constant tau is equals to R multiplied by C.
Isn't that 1 over RC?
No, that's for inductor. One R over L. That's for inductor.
That's for inductor?
R over L. But I guess for
No,
RC.
One
For
over
inductor
RC.
is L over R, and for capacitor is RC.
It's directly RC.
In expression is T over tau.
Okay, that gives us the time constant.
Yeah.
Right? sir?
So the time constant is much smaller in case of graphenes. So we get faster clock speed also.
So we can switch faster.
Yes.
Right? Yeah. So in terms of, it has to be single layer, right?
Yeah, so far because
So when we compare with copper, for example, copper has a certain thickness
okay.
which we don't have in this case. It's single sheet.
Yeah, but we can use multi-layer also.
You use multi-layer. So then high current causes electromigration. And here
Right.
also is high current.
Yes.
And at the edge we have these dangling rods, don't we? What do you think of electromigration? How is there chances? Because there are defects at the edge.
Well, so far all the papers I read, I didn't find that much issue with graphene with electromagnetism. I think this was mainly an issue for the silver interconnects. Then
But
comes
whatever they use, isn't that wide enough to not matter? But if you were scaling it down, you might want to make them thin and quick.
Well, to be honest, I have not found any issues so far with my research.
Of course, if it was there, we wouldn't be discussing it. That's why I'm
Yeah.
thinking of that. So, how easy is it to make an oxide of that?
I do not find that yet.
I have one more question.
Sure.
So usually electric device is affected by electromagnetic interference, right? Like for example, the sun make a strong radiation that device affected by the radiation, right?
Yes.
So is interconnection.
You're talking about EMI. That's
Right, right. So if you reduce size, that is affected by more affected by that interference. I don't know. It's just like curious.
But I don't know what's the actual dependency with the size of the conductor and the EMI. But since we are observing less capacitance and resistance for graphene, I guess the EMI could be less also. I don't know the actual mechanism why EMI increases for decreasing size. Is it because of the increased capacitance or the increased resistance that we see for usual conductors, usual metal conductors? If that's the case, then graphene will surely perform better.
Right? That's dangerous. Right. Keep this right. Right, so that's one important part done. Strokes. So if everybody uploads their PowerPoint today, I'll post the grades for this. Then we'll have a week for regrade requests. Now would be the best time to get our scores in place. So I'll be, by probably end of this week, send you Excel worksheet with all your grades so far to take a look to what you call reconcile any discrepancy. If you see something that's supposed to be there and it's not there, we can discuss those. Right? So yeah, graphene is something which we'll see in interconnects that we like to grow a thin oxide on metals just to passivate it. So there's no further interaction, there's no further reaction of that metal. So we do oxidize those metals, very thin part of it. But with graphene, there's no such protection. If you oxidize graphene, basically it's already single layer, a few layers. So you are getting a very large percentage of that conductor used up for that.
Can you even oxidize graphene? Doesn't that just become carbon dioxide?
No, it's graphene oxide.
Really?
So yeah, there's dangling oxygen atoms that bind to it.
How thin does something have to be graphene instead of graphite?
Single layer.
Single layer.
Few layers. So what they do is they stack graphene layers, physically stack them. So these are not chemical stack. If they chemically stack, then it becomes graphite. Then it loses that.
But again, we can deposit dielectric layer also.
Right. So you can put
Instead of growing,
yeah. So you can decorate those bonds which are raised for passivation. But yeah, it's lots of interesting work coming out on this. So it's always something new coming out. So let's get back on track on CVD. And we had a few lectures left. When is the final? 10th of May. And this is already what? 20th? 19th? 20th? 19th. Okay, we get 3-4 lectures left. Right? So this is exactly what we have. We briefly touched upon these when we started. That's what does CVD do? CVD or H. Essentially, we pump in reactants. They result into some products. The product get deposited on a surface. So surface is there. So there are a number of reactions that occur in there. It might be a reaction which occurs in gas phase. It may happen on the surface. But essentially, you get those reactants on the surface, and they react and start building a nucleation site. So nucleation site for many of these, from all of the deposition processes, we have a small sort of dots that form and then they grow. So those dots are called nucleation sites, where the first deposition occurs and then it grows, and then many of those, when they join each other, they form a film. That's why we call that minimum thickness we say, okay, that is what will create a monolayer. If we are below than that thickness, we will not get a monolayer. We'll get patches of those growing films, but not monolayer. So this is what we call a nucleation, and then this island grows and they ultimately cover the whole surface. This happens in CVD, this happens in PVD as well. The difference in PVD, we are physically depositing whatever we have. In CVD, we are depositing the product. Right? So, and the byproducts have to be pumped out. If we don't, and byproduct is a polymer, we'll get them to redeposit on that, which will cause contamination and cause the loss of integrity of the film. So we have to pump it out as it happens. Now, once we get the exhaust out, there may be products which we have to monitor, like silane. Silane is hygrophobic. What is hygrophobic?
Ripples.
Ripples?
Repellent to water.
Pardon?
Repellent to water.
Ripple into water.
Ripples water.
Ripples water. Contact. It reacts with water aggressively, so it causes a blast. So there's hygroscopic, something that reacts with water.
Is it hydrophobic or hygroscopic?
Hygro, not hydro. Hydroscopic hydroscopic would be something which you use with water. It's hygro. So, but anyway, there can be species which we really have to monitor their flow. We have to monitor how much of that is coming up, because that can also tell us the reaction that's happening inside, the quality of that reaction. So, how do we provide the energy for that reaction? So, it can be thermal, photons, electrons. And most typical is thermal, but many cases we can't heat up a wafer to really high temperatures. In that case, we use plasma. So that defines that PECVD and LPCVD. One is plasma enhanced CVD, other is low pressure. So the reactions can be pyrolysis, reduction, oxidation, and what we want to achieve in that is we can get a film deposit in a very short period of time. So if you want to grow oxide, and we heard that thick oxide growth is a challenge, somebody presented that paper, but we can deposit oxide really fast with LPCVD. It will not be as high quality as you can get with dry oxidation, but can get a decent oxide.
What's disproportionation?
I don't know what is this. Oxidation disproportionation. Probably the reaction results into different species getting consumed and some not.
I see.
Have to look at it. So, okay, why do you want to do this? So, can we want to do it quick? We don't want to harm the layers that we already have. Simple example is if you have a metal there already. We can't do oxidation, right? We can separate them. But we can do PCV. We can use plasma to do deposition without harming what is already there. And we don't want contamination, so we want to have all the byproducts to pump out from the chamber. So these are some of the recipes that we use. It's silane, mostly is silane for silicon. See difference between the method LPCVD, PECVD, or APCVD. So they all are happening at different temperatures. Can you see something in terms of temperature for PECVD and LPCVD in these recipes? Generally, LPCVD temperatures are what?
A little bit higher.
Higher. Right? So LPCVD temperatures are, and PECVD temperatures are generally low. Right? So this tells us, okay, what kind of tolerance we have that will dictate what process we can do. So we can deposit silicon dioxide by PECVD, LPCVD both, but depending on what we have there will define what we want to do. And then there's this question of coverage as well. What kind of material we have on the surface that we want to do. APCVD is what you call, this is the least rigorous. It's, I don't know what is A stand for, I'm forgetting. Atmospheric pressure CVD. That's doing that. Huh? Which one is faster? Would depend on your recipe. So you'll have to see your recipe. LPCVD is generally slow.
So if I
But still, your reaction, your recipe, so outcome of recipe will define which one. So recipes are different deposition rate.
So does this mean if I had a regular oven at 300 degrees and I open some silane into it, I'd still get some deposition with that?
Yes, and a big blast. Right, so these are very well controlled, and once how much we pump in the chamber is very well controlled. Right, so something which is missing is there are some parameters which are missing, of course, the pressure, and which is measured in SCCM, and what are the byproducts we expect from them. So the quality of film is not the only factor, the morphology, which of course we know now that if you get good step coverage or bad step coverage, so that also comes into play, depending on aspect ratio, depending on how much tolerance we have at the edges, how much filling can it do. So all these factors also come into defining a deposition process. So when the reaction of these occurs in the gas state, we call that homogeneous process, especially in this case. But if the reaction occurs at the surface, we call it heterogeneous process. The simple reason is that if the reaction occurs and you have product made, now the whole product is going to cover. So you have product homogeneously coming. But if the reaction occurs on the surface, then it depends on reactants coming together on that surface. So your film may not be heterogeneous. But once we get the monolayer form, once all those islands go and catch up with each other, then we get a uniform film. Then we don't. But for that case, we have to have a thick enough film to overcome those issues. Does that make sense? So this is how it starts, deposition. So you get one molecule deposited, and that gets another one. So you have this small nucleation site where it starts growing.
So it's possible until we obtain one single monolayer, there's possibility that we might get ununiform.
So you might not have deposition at some. So you'll have patchwork all over the place. You'll have patchwork.
So does the homogeneity mean uniformity here?
No, coverage. It has to cover the whole surface. Then uniformity is what you will measure at roughness. What is the roughness of that deposition, right? So it may be thick some places, it may be thin at some places. So that's also something which is part of the CVD process. In this case again, we have a growth model defined by groove, so which basically defines that there is a step that's formed at the edge, and then so step if I'm depositing. So I have this nucleation site, so this is a step. Now they join on top of that, and ultimately what we end up is the whole coverage of the surface with that. And it predicts the growth rate, and it says that there's only two steps: reactants getting on the boundary layer and the reaction with the surface. So first is it gets to that. The second is it binds to the bottom, to the surface. And this again, now if you remember the model we had, Tailgrove's model, we had a number of limitations in the diffusion, right? So first it had to get on the surface, then it had to travel through the oxide, then it get on the other side, and right here we don't have those barriers. So our only flux is F1 and F2. How quickly can we bring it to the surface and how quickly it can react. So there's, unlike oxidation where we had those diffusion through oxide, which was a limiting factor, we don't have that. So it's a simplified form of Grove's model. So when you plug in those values, in case of F1, it's the mass transfer coefficient that defines that flux, and in case of F2, it's the reaction rate constant, yes, which defines how fast we can continue. In a steady state, we can equate those, and we get a relation for the concentration of the reactant at the surface, which is a nice equation to remember. So in both cases, we have the point to remember in this discussion is what factor will be the limiting factor. What if is it going to be the Hg that is going to be the limiting factor, or Ks? Because both will then define what is the concentration at the surface.
What's Hg again in this?
Hg,
Yes. Cascade mass.
the mass transfer. So now, where are we getting from here? In one case, suppose I have two processing exactly identical. In one case, I'm pumping less gas. In one case, I have heated up 100 degree higher. So 100 degree higher means I'm giving much more energy to the reaction. In this case, I'm pumping in less gas and 100 degree less. Which one is going to be fast reaction? Which one is going to have more deposition rate?
The one
Which is warmer, right? Now, if I reduce the gas pumping in this one and I reduce the gas pumping in this guy, which one is going to be slow? Same temperature, we have less gas in one, we have more gas in the other. The one which less gas will have high deposition rate.
Slower.
Will have less deposition rate, right?
Yes.
Right. So these are two factors. If I can't heat up my wafer, I can't have, my reaction will be not reaction rate limited because I'm not going to heat it up too much. But in that case, it will be limited by how much gas is supplied. Right? But if I have LPCVD where I heat it up, that's where my reaction is limited by reaction rate. I can supply all the gas I want unless the reaction is consuming it, it's not going to matter. So in both cases, one case mass transfer is reaction rate limitation, the other case the reaction is the deposition rate limitation. Right? Make sense? So, yes, ma'am.
According to Grove's oxidation growth model, after a certain thickness, the growth rate decreases because it needs to permeate through. In case of deposition, we shouldn't be seeing that, right?
No.
So it will never slow down. It will always be linear.
It will always depend on how much we are pumping in and what's the rate of reaction. Just on that.
Yeah, but it will never be diffusion rate.
There will be no diffusion.
No diffusion.
Yeah, there will be no. So that's why it's just F1 and F2. But now these two are limiting factor. One is the limiting factor in PECVD, where it's not high temperature, but it depends on how much we pump in. The other case, it's going to be the temperature dependent, how much energy we supply to reaction.
So is the film going to be crystalline or amorphous or polycrystalline?
We can get polycrystalline. If we just remember, there's only one way how we get crystalline films. What is that? Epi, right? Epitaxial. We can get polycrystalline, but not polycrystalline. Right? So let's stop there. We'll continue here from this guy's and we'll see